Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
So I want you to just picture looking back to a time when the universe was, well, essentially an infant, like less than 1 billion years old.
Right. A very different place than it is today.
Completely different. The cosmic web is just unbelievably dense and volatile. And at that incredible distance, specifically at a redshift of 5.7, we are witnessing this literal cosmic dance between two of the brightest, most violent objects in existence.
It really is staggering. We are talking about the system J20374537, which is a confirmed spatially resolved dual quasar.
Yeah, and that's the whole mission today, to unpack what these colossal engines actually are, and how astronomers even prove they weren't just some cosmic optical illusion, which is a huge part of this story.
Oh, absolutely. Proving what is actually real in a universe that is just full of mirages is half the battle.
Exactly. Because when we talk about peering that far back, it's not just distant trivia. It's a full-on detective story for you, the listener, about the invisible fabric of the universe itself. But I just keep getting stuck on the awe of the sheer distance.
I mean, you have to. The improbability here is off the charts. When we look at quasars at a redshift greater than 5, we are already looking at the rarest, most extreme objects in the early universe.
Just finding one is a big deal.
Exactly. So finding 2 of them, separated by just a few kiloparsecs, locked in this violent gravitational spiral, it's basically absurd.
It really is.
I mean, this is literally one of only 2 confirmed quasar pairs we have ever found at a redshift that high. It forces us to completely reevaluate our models of how fast these supermassive black holes were growing during the cosmic dawn.
But there's a paradox here, right? Because the whole hierarchical model of cosmology, the idea of how structures assemble, it basically says galaxies should be slamming together all the time in the early universe.
That's right. The early universe was crowded. Mergers were common.
Right. So if galaxy mergers are happening all the time, why is finding 2 blazing quasars in a single system so extraordinarily rare? I mean, shouldn't the sky be lit up with these things?
Well, it comes down to a really brutal timing problem. A galaxy merger is a slow, agonizing process. We're talking hundreds of millions, sometimes over 1 billion years, to actually complete.
Which is a massive amount of time, even on a cosmic scale.
Exactly. But the active quasar phase, the part where the black hole is actually eating and glowing, that is highly transient.
It doesn't last long at all.
No, the supermassive black hole only accretes matter fast enough to outshine the whole galaxy for a tiny fraction of that merger timescale. The duty cycle might only be a few million, maybe tens of millions of years.
So it's kind of like having a spectacularly lazy, picky eater of a black hole, right? It just sits there dormant until a galactic collision forcefully shoves this cosmic buffet right into its mouth.
That is a very visceral way to put it, but yeah, it's accurate. In a normal stable disk galaxy, the gas is just orbiting smoothly. It's supported by its own rotation.
You're not just falling in.
Right? It will stay in orbit practically forever unless something violently extracts that rotational energy. And that's what the major merger does. It provides these extreme gravitational torques.
It disrupts everything.
Exactly. It creates these massive shocks, funnels unimaginable amounts of gas straight down into the nucleus, but the accretion isn't smooth. The gas piles up, the quasar ignites, and then the radiation pressure from the quasar itself creates these massive outflows.
Oh, right, the feedback loop. It basically blows its own food source away.
Precisely. It chokes off its own fuel. It suffocates itself. So to catch J20374537 with both supermassive black holes actively lit up at the exact same moment, from our perspective, 12.8 billion light years away.
It's wild.
It's like catching 2 separate lightning strikes in the exact same photograph.
And because it's that incredibly rare, the initial reaction from the scientific community wasn't just, popping champagne. It was profound skepticism. People thought it was a trick.
Oh, the scrutiny was intense. Because when this was first reported as a candidate back in 2021, observers just saw 2 identical, incredibly bright dots separated by a tiny fraction of an arcsecond.
Right.
And when you see that at redshift 5.7, the default assumption in astronomy is absolutely not a binary quasar. The default assumption is an optical illusion caused by strong gravitational lensing.
Which we really have to unpack because gravitational lensing is such a common imposter in deep space observations. It forces astronomers to second-guess their own eyes constantly.
It really does.
Yeah.
General relativity tells us that massive foreground objects like a galaxy cluster
Hmm.
literally warp the space-time around them.
Right, it acts quite literally like a massive invisible glass lens.
Exactly. So if you have a single solitary quasar way in the background, its light passes through that warped space-time and gets bent. And that geometry can easily produce 2 or even 4 separate images of the exact same quasar.
I always think of it like looking through a distorted funhouse mirror or like the curved bottom of a wine glass. You hold up one candle, but through the glass, it looks like 2 distinct flames.
That's a perfect analogy. And because it's just a mirage of the same object, the light from those 2 dots will look identical.
Right, their spectra match perfectly.
Exactly. Their redshifts, their colors, everything matches.
Mhm.
And the degeneracy there, the difficulty in telling them apart is just notoriously hard to break.
But wait, I want to push back on that a bit. If you're looking at 2 identical dots of light from billions of light years away, and a literal cosmic funhouse mirror can perfectly fake that image, how can you possibly prove what you're looking at is real?
Well, in traditional optical astronomy, it's incredibly difficult because the deflector galaxy, the lens itself, might be completely hidden by the blinding glare of the quasars.
It's buried in the light.
Right. So you look at the optical data, you see 2 bright dots, you extract the spectra, and they're twins. Photometrically, a lens system and a real binary look exactly the same.
So if you can't see the lens, you can't map the distortion. It sounds like a total dead end.
It is a dead end if you only look at the point sources. The rigorous burden of proof here requires you to look away from the bright lights. You have to look at the dark space between the quasars for physical interactions that a mirage couldn't possibly fake.
You have to find the physical wreckage of the collision.
Precisely. A gravitational lens will distort the background host galaxy into smooth arcs or a ring, but it will never create localized, chaotic, asymmetric wreckage between 2 independent gravity wells.
Because a mirage doesn't leave muddy footprints connecting 2 houses.
Exactly. But to see those footprints, you have to completely bypass the brilliant optical light of the quasars. You have to move to the far infrared and submillimeter wavelengths to see the cold gas.
Which brings us right to the smoking gun. This is where the team, led by Minghao Yu, brings in ALMA, the Atacama Large Millimeter Submillimeter Array.
Right. ALMA is the perfect tool for this. Its spatial resolution at submillimeter wavelengths is just unprecedented. They weren't looking at the black holes at all. They were mapping the cold, neutral gas of the host galaxies.
And specifically, they were mapping the emission lines of ionized carbon, which is noted as C2. I really want to dig into this because why map ionized carbon specifically? What makes this exact element the perfect cosmic fingerprint here?
It really is a phenomenal diagnostic tool. It's tied directly to how galaxies form stars. See, in a galaxy, gas has to cool down before it can collapse under gravity to form a star.
Right, if it's too hot, it just expands.
Exactly. And when young, massive stars are born, they blast the surrounding area with ultraviolet radiation. That UV light hits dust grains, ejects electrons, and those electrons bounce around and heat up the gas.
So the star formation is heating the gas, which should stop more stars from forming. It needs a release valve.
It absolutely needs a release valve to radiate that energy away. And carbon is perfect for this because it has a very low ionization potential. Even in cold clouds, carbon gets ionized easily by starlight.
Okay.
So those bouncing electrons hit the ionized carbon atoms, exciting them. When the carbon atom drops back down to its normal state, it releases a photon at a very specific wavelength, 158 micrometers.
Ah, so that specific flash of light is the cooling process happening.
Right. By mapping that 158 micrometer emission, you're literally mapping the cold gas reservoir that fuels the whole galaxy. And the best part is, at that wavelength, the light punches right through the dust that blocks our optical telescopes.
It cuts right through the glare. So they point ALMA at this system, they look for that specific carbon signal, and they find an absolute mess.
They found a massive tidal bridge. It wasn't just 2 neat pools of gas around the black holes. There was a physical, contiguous stream of cold interstellar gas stretched across the space between them.
Ripped out by sheer gravitational violence. But let me play devil's advocate for a second. Couldn't a skeptic just say, well, maybe the lens is incredibly complex. Maybe a weird foreground cluster is magnifying a background spiral arm to just look like a bridge?
That is exactly the kind of rigor the community demands. But LMA didn't just give us a static picture, it gave us kinematics. It showed us exactly how fast the gas in that bridge was moving.
Because of the Doppler shift.
Exactly. They mapped the velocity field, and they found complex, chaotic, non-circular motions. A lensed spiral arm would still look like a spinning disk, just distorted.
You would have a neat, orderly rotation.
Right. But this was total kinematic chaos.
Yeah.
It was definitively the signature of two massive gravity wells tearing each other apart. The optical illusion theory was officially dead.
Wow. So we are genuinely looking at two immense galaxies in a death spiral, and finding this bridge of star-forming gas just naturally leads us to the realization that these black holes aren't just destroying things.
Far from it.
Right. They are residing in galaxies that are frantically creating new stars. These are literal star-forming factories. The ALMA data show that these host galaxies are incredibly massive.
Oh, they're behemoths. The dynamical mass calculations show that each of these merging components is at least 10 billion solar masses.
10 billion. At redshift 5.7, that is highly evolved. We aren't talking about tiny dwarf galaxies bumping into each other.
No, these are massive systems. But the number that really jumps out is the star formation rate. The data suggests they are churning out over 500 solar masses of new stars every single year.
500 a year. I mean, just to ground that, our own Milky Way produces what, maybe 1 or 2 solar masses a year?
Yeah, about 1 to 2. So J2037-4537 is operating in an overdrive that is hundreds of times more intense than our own galaxy.
It's like an assembly line running at a dangerous, frantic pace. If you were floating in the halo of one of these galaxies, the sky would just be a chaotic mess of ultraviolet light from massive young stars blowing up in supernovae.
It'd be an incredibly violent engine of creation, yeah.
But I do want to push back on that 500 number for a second. Because the researchers explicitly mention systematic uncertainties regarding dust temperatures. If our calculations rely on assuming the temperature of invisible dust billions of light years away, how wildly could these numbers swing?
That is a fantastic question, and it's a critical caveat. When we measure star formation rates with ALMA in this way, we are actually measuring the thermal glow of the dust.
Right, the dust absorbs the starlight and glows in the infrared.
Exactly. And to calculate the total mass of that dust, and therefore the star formation, we have to assume a dust temperature, usually around 45 Kelvin for these early galaxies.
But it's an underdetermined system, right? We don't have enough data points to know for sure.
Right. We only have a few data points on the spectrum. So what if the incredible radiation from the quasars and the sheer violence of the starburst has heated that dust up to, say, 65 Kelvin instead?
Oh, because of the Stefan-Boltzmann law, hotter things radiate way more energy.
Exactly. It scales to the 4th power of the temperature. So if the dust is hotter, you need significantly less dust mass to produce the bright glow we see.
And if there's less dust, there's less gas, and your 500 solar mass figure might be a massive overestimate.
It could be off by a factor of 2 or 3, easily. On the flip side, if the dust has a different chemical composition, maybe more silicates in the early universe, the real rate could be even higher.
Are we looking at a conservative baseline, or could we be drastically overestimating the chaos?
We won't know the exact number without follow-up observations, maybe using the James Webb Space Telescope combined with deeper ALMA maps. But honestly, even if the rate is 300 instead of 500, the physical reality is the same.
It's still an extreme starburst system.
Exactly. The merger is violently compressing the gas, fueling the quasars, and sparking a massive, rapid assembly of stars all at the same time.
It's just spectacular. So we've established the massive scale, the violent waltz they're locked in. But this dance has a grand finale, right? A finale that won't happen for a very, very long time.
A very long time. Right now, at the moment we observe them at redshift 5.7, these supermassive black holes are still separated by thousands of light years. They aren't a true binary system yet.
They still have to navigate this incredibly chaotic, turbulent soup of gas and stars just to get to each other. How do they actually close that gap?
The main driver at these large scales is something called dynamical friction. As the black hole plows through the dense background of the galaxy, its gravity pulls on the stars and gas around it.
It deflects their orbits.
Right. And as the black hole moves forward, it leaves behind a localized cluster, a wake of all that material it just pulled on.
Oh, so it's literally dragging a heavy tail of stars behind it.
Exactly. And the gravitational pull of that trailing wake acts as a constant brake. It saps the black hole's kinetic energy, forcing it to slowly, relentlessly spiral inward.
And the models say this dynamical friction process is going to take a staggering amount of time for J23O374537, something like 2.1 billion years.
Right. It will take over 2 billion years for them to finally become a gravitationally bound binary, which would happen around redshift 2.
But just getting to the center isn't the end of the story. Once they get really close, like within a parsec of each other, that friction stops working, doesn't it?
It does. It's called the final parsec problem. The volume of space gets too small to hold enough background stars to create that drag.
So how do they keep falling inward? Do they just stall out?
If it were a dry merger without gas, they might stall. But here, they enter the hardening phase. The binary acts like a giant gravitational baseball bat. Any star that wanders too close gets violently ejected from the galactic center.
Oh, wow. It just slingshots stars away.
Exactly. And the energy to kick that star out comes from the black hole's orbit, so they step slightly closer together. But eventually, they kick away all the stars in the center. They run out of ammo.
Right, they clear out the whole core. So what bridges that final gap?
The gas. Because this is a very wet, gas-rich merger, the black holes are swimming in a massive circumbinary accretion disk. The sheer viscous friction of that gas provides the drag needed to push them down to milliparsec scales.
And once they get that close, separated by mere light months and moving at a huge fraction of the speed of light, physics fundamentally shifts.
Yeah.
General relativity totally takes over.
Absolutely. At that point, the dominant way they lose energy is by radiating gravitational waves.
Ripples in the literal fabric of space-time. And this connects our ancient redshift 5.7 quasars directly to the most cutting-edge physics happening right now on Earth. Because these aren't the quick, high-frequency chirps we hear from small black holes with LIGO, right?
No, not at all. A supermassive black hole binary takes millions of years to unspiral. The gravitational waves they produce have incredibly long wavelengths. We're talking nanohertz frequencies.
So the wave takes years just to complete a single oscillation. You can't catch that in a laboratory.
No, you need a detector the size of a galaxy.
Which is exactly what pulsar timing arrays are. It's brilliant. We use millisecond pulsars, these rapidly spinning dead stars that shoot radio beams at Earth with perfect precision, like cosmic clocks.
They are staggeringly precise.
And if a massive nanohertz gravitational wave rolls through the Milky Way, it actually stretches and squeezes the space between Earth and those pulsars.
Right. The distance the radio pulse has to travel physically changes.
Which means the pulse arrives just a tiny fraction of a microsecond early or late. And by monitoring dozens of these pulsars, scientists act like a giant cosmic seismograph listening for that rumble.
Exactly. Groups like Nanograph have actually found compelling evidence for this recently. A stochastic gravitational wave background. It's a constant low-frequency hum vibrating through the universe.
It's the combined noise of millions of supermassive black holes slowly spiraling together across all of cosmic time, like the low rumble of distant traffic in a busy city.
That's exactly what it is. But here is the kicker. The background hum they detected is actually stronger than our baseline models predicted.
Wait, really? So if it's louder than expected, does that mean our fundamental ideas about how crowded and violent the early universe was have just been too conservative?
That is the leading theory right now. A louder hum means there are either more supermassive binaries out there, or they're much more massive than we thought.
And that brings us right back to J23.74537.
Exactly. Yeah. If massive, chaotic, dust-enshrouded early mergers like this are more common than we realized, which optical surveys missed because of the dust, then they could be the exact source of that extra gravitational noise.
Wow, it's a perfect loop. We use the submillimeter ALMA data to prove the quasar pair exists and cut through the optical illusion. And that proves these massive early mergers happen, which perfectly explains the invisible gravitational hum vibrating through our detectors right now.
It links the entire history of the cosmos into one mechanical framework.
It really does. I mean, we started with a suspicious tiny dot at the edge of the observable universe. We unpacked the invisible ionized carbon, mapped the tidal wreckage of galaxies churning out 500 stars a year, and tracked their brutal 2.1 billion year orbital decay.
And the timeline of that decay is it's fundamentally hard to wrap your head around.
It is, because we are observing them at redshift 5.7. The light we just analyzed has been traveling through expanding space for nearly 13 billion years. But the actual physics we just talked about, the friction, the scattering, the final merger, only takes 2.1 billion years.
Right.
Which means, from an objective standpoint, the future of these black holes is already ancient history. They merged over 10 billion years ago.
That grand finale happened before our solar system even existed.
Exactly. The immense burst of gravitational waves from their final collision was injected into spacetime billions of years before the Earth formed. Yet because those ripples travel at the speed of light, just like the photons, those exact shock waves are still racing toward us right now.
They're still in transit.
It's mind-bending. When you look up at the night sky, you aren't just looking at stars. You are literally wading through a sea of invisible shockwaves from colossal collisions in a universe that doesn't even exist anymore. The echoes of J20374537 haven't even washed over us yet. We are literally just waiting for the ripples to arrive. What other invisible ghosts of the ancient cosmos are watching over us right now?